When you stand on a weighing machine, is it telling you your mass or your weight? Let's uncover this mystery with a little experiment. Here I am stepping on this weighing machine. It shows approximately 60 kg. But wait, what if I could teleport to the moon and now the machine says 10 kg? Wow, I've shed 50 kg in seconds. Hold on, this doesn't mean my mass has changed. Mass remains constant no matter where you are in the universe. The real reason for this change lies in what weighing machine measures, that is your weight. Weight is the force of gravity pulling you down. On Earth, my weight is 600 Newton. The weighing machine cleverly divides that weight by value of gravity on Earth, that is approximately 10 meter per second square, to display my mass as 60 kg. On the moon, where gravity is weaker, my weight drops to just 100 Newton and the machine recalculates to show 10 kg. Pretty neat, right? So, weighing machines don't actually measure your mass, they measure your weight and use gravity to convert that into mass reading in kilograms. Want to learn about more? Let's dive in. But students, before we start, please don't forget to like, share and subscribe to our channel. Let's learn together. Hello students, welcome in today's class. In today's class, we are going to discuss the various important types of forces. Also, in our class today, we are finally going to discuss motion under gravity in detail. So, if you remember, when we were discussing the chapter motion, we did not go into the details of motion under gravity because that needed the knowledge of forces. That is why we will talk about that topic in today's class. Alright. So, there is a lot to learn and you should be very excited about today's class. So, I will wait and then we can start. Alright. So, the first thing that I wish to talk about is the force of gravity. Okay. So, the first force that we are discussing today is the force of gravity. Let's keep it very simple. The pull of gravity on an object is called the weight of the object. Okay. So, any force, any object, the force that it experiences due to gravity is called its weight. Alright. So, it is a force and that is why its unit should be Newton. Alright. The second is the contact force. So, I am just giving you a brief of all this. So, if for example, you are looking at this person, the weight is acting in the downward direction, that's because of gravity. And as that person is going or being pulled down, why is he not moving further down? That means some force is balancing that force of gravity. So, that is called the contact force. What is that called? Contact force. So, any force that results due to contact between two objects is called the contact force. And that is always a pushing force. That is always a pushing force. So, the ground is pushing the person upwards while the person is pushing the ground downwards, again following Newton's third law. So, contact force is always first a pushing force, second it is always perpendicular to the surface. So, can you realize this here? The surface is, let's say, in the x direction, then the contact force will be in y direction. Let me take one more example to clear this off. So, let's say you have an inclined plane, you have a wedge, alright, and you place let's say an object here of mass m, okay, alright. So, now the contact force will be like this, keep that in mind. So, this block will push the ground like this while the ground will push the block like this. So, this is force pair, okay, equal and opposite force. So, this force is the force on the block due to the inclined plane and this force is the force by the block on the inclined plane, but it always acts perpendicular to the surface. That is why sometimes we also call it as normal contact force and denoted by N. Okay. So, keep that in mind. So, two basic forces, the force of gravity, that is the weight, and the contact force, that you can understand. Contact force is a force that is applied by the objects in contact with each other. Two things, it is always a pushing force, it can never be a pulling force. Second, it always acts perpendicular to the surface. Keep that in mind. I will wait here. You pause the video, write down the important stuff, and then we move forward. Alright. So, the next thing, gravitational field strength. So, just as we were discussing that there is a force of gravity that is obviously going to be different for different planets. Isn't that very obvious? That the pull of any planet is not going to be the same as that of the Earth. So, just keep that in mind. So, to accommodate that, we have a term called the gravitational field strength. As the name implies, it tells you the strength with which any planet is capable of pulling objects. Okay. So, how do you define that? Just apply unitary method, and it is defined as the force per unit mass any planet would apply. I will repeat again, force per unit mass or weight per unit mass. Okay. So let's say for the case of Earth, just to give you a brief, this is approximately 10 or you can say 9.8 Newton per kg. Okay, so for every kilogram, Earth applies a force of 9.8 Newton or approximately 10 Newton. So if it is a 2 kilogram block, then the force is going to be 20. If it is 3 kilogram block, then it is going to be 30 and so on. So can we say that the weight is nothing but m times g, because g is telling you, this is telling you the gravitational field strength, that is the force for unit mass. So whatever the mass is, you just multiply it by that. So if it is 3 kilogram, then it is 3 times 10, that is 30. Okay. One more thing that you should understand, since you are writing gravitational field strength as force per unit mass, this can also be taken as acceleration. This can also be taken as acceleration. So if you release anything and it falls, then you call it the acceleration due to gravity. But mathematically, they both are the same. So gravitational field strength is also force per unit mass, and acceleration due to gravity is also force per unit mass. Okay. So the unit is Newton per kg, or it can be meter per second square. Just to give you an idea, that moon has a gravitational field strength of 1.6 approximately. So on moon you would feel lighter, okay, and the value of gravity over there is almost 1/6 that of the Earth. So if you take any object that is on the Earth to the moon, then it will definitely feel lighter, and that is why the astronauts can also jump to a higher height, because the pull of the gravity on the moon is a bit less, okay, quite less, in fact 1/6. Okay, so weight, your weight on Earth is going to be different, but on the moon it's going to be different. But do remember, mass will not change. Mass is the amount of matter that does not change. Mass is same on Earth as well as moon. What changes is the gravitational field strength, and because that changes, the weight will also change. Keep that in mind. So mass is independent of the planet. Some more facts you can know, that the Jupiter planet Jupiter has maximum gravitational field strength in the solar system. It's approximately 25 Newton per kilogram. So approximately 2.5 times that of the Earth. Okay, so different planets have different capacity. Earth has approximately 10, Jupiter has 25. All right, so far so good. And one last thing, just for an idea, that weighing machines also measure weight, but they show you mass. Now what does that mean? So weighing machines, they have a function that they will measure the force that you apply when you stand on them, but when they measure the force, they show you mass. It's quite awkward. Weight is a force that is measured in Newton, but mass is measured in kilogram. So they have a calibration. They calculate the weight first, then divide it by g, and then show you the mass, because weight is equals weight divided by gravitational field strength is going to give you the mass. So keep that in mind, just for the sake of knowing it. You might have a conceptual question on this. Two things: weighing machines measure weight, but they show mass by dividing it by acceleration due to gravity or the gravitational field strength. One more thing, that if you go on different planets, the mass is going to be the same, but your weight is going to be different. Alright, so there's a lot to learn here. I will wait and then we move forward. Okay. So, some more common types of forces. There is friction, and friction also we will talk in two parts. One is friction between two solid surfaces, okay, just like you can imagine a block on the ground, and when you start pushing it on the ground, okay, so when you start pushing it on the ground, let's say with some velocity v, then the force that it will experience is called the force of friction. Okay, so there is frictional force that can be related with the roughness of the surfaces. It depends on both the types of surfaces, and there can be many ways of reducing this friction, like oiling, using some lubricants, right, ball bearings and stuff like that. So you can reduce this friction, rollers, okay, all these things. So the force that acts when two surfaces rub over each other, or there is a tendency for that. So that is also very important. Sometimes you might not see two surfaces rubbing over each other, but still there is friction. For example, let's say if this is a block and it is lying on the ground, listen to this very carefully, and you apply some force, okay, and that force is very minimal and the block does not move. The block does not move. What is that supposed to mean? That, you know, the block is not changing its state of motion, so definitely it is being balanced. So who's balancing that? Friction. The friction is also there when there is a tendency for motion, okay, keep that in mind. So it's not always that the surfaces should rub and there is a motion, but it can also be when there is a tendency of motion, okay. One more thing, that friction do produce some heating effect. You can rub your hands, and if you will ultimately feel that your hands are getting hotter, like the temperature is increasing, so it does produce heating effect, and that is the reason of sometimes unnecessary energy loss as well. So sometimes it is an evil that it works against us, but at the same time it is very important for us, because if we have to walk, right, if I have to hold this, I would need friction. If friction is not there, I won't be able to hold on to this will slip. If I have to write, I need friction, okay. So keep that in mind, so that it is necessary also, but sometimes it is evil also, okay. Now if we bifurcate it into two parts, if it is happening through air or water, that is like air or liquids, that is fluids, then we call it the drag force, okay, then we call it the drag force. So forces of friction when an object moves through air or water is called the water, or you can say liquids, then that is the drag force, okay. So for example, that's why I've taken this car. So when this car is moving on the road, it's suffering both kinds of friction, one due to the road, that is the solid friction, and also because of the air, air also is playing a role, and this is providing the friction, that is called the drag force. Two things that you should know before we move forward about air resistance is that this force of air resistance, all right, is proportional to the velocity. Very important. So if you are going at a faster speed, at more speed, then you will suffer more air resistance. But if you are going slow, then the air resistance will be less. And it is very logical. If you go into the depth that what is the real cause of air resistance, so you would say when you are moving, you are continuously colliding with the air particles. So those air particles is kind of providing you that opposite force, which is kind of a hindrance in your motion. So if you move at a faster speed, at a more speed, then you collide with more particles in a particular duration, and that gives rise to more air resistance. Also, this air resistance is proportional to the area of contact, okay. So the area, so for example, if I have two choices, like one is a blunt shape and the second one is the narrow shape, which you call streamlining. So who will suffer more air resistance? The answer is going to be blunt one. Why? Because if it's the blunt shape, then you are colliding with more particles, and that is the reason that air resistance will also increase. So keep it in mind that there are two things: air resistance is proportional to the velocity and the air resistance is proportional to the area. All right, I will wait to for you to copy down some important things, though we will be sharing the slides with you as well, so there is no need to worry. But still, I will wait, you pause the video and write down the important stuff, and then we move forward. All right, so the next thing is the upthrust or the buoyant force. Okay, so the upthrust is obviously something you must have felt when you are in a swimming pool. You do feel lighter. Okay, so I will not go into the detail of this, but just to give you an idea that the pressure at lower depth is more than the pressure at higher, like the pressure at lower layers, or you can say more depth, is higher than the pressure at upper layers. So this difference in pressure causes a net upward force on you, and that is why whenever you have some heavy object, you put it in a swimming pool, kind of while it is in the swimming pool, you will feel that it is lighter. The reason is that the liquid is pushing the object upward also. So let's say this is some liquid, just to explain this a little more. Okay, and this is some object. So the liquid here is, let's say, giving a pressure P1, while the liquid here is giving a pressure P2. So as you will learn, or you may have learnt, that pressure increases with depth. So this pressure P2 is going to apply more force as compared to P1, just to give you an idea. This results in a net force in the upward direction, and that is why any object which has some weight will feel some force of gravity. Inside water, it kind of feels little less than what it is in the air. The reason is not that the effect of weight is diluted, it's just that because of the upthrust provided by the liquid. So keep that in mind, the upward push of a liquid or a gas for that matter. So though it's very prominent only in case of liquids, but let's say there is a helium balloon, let's say there is a hot air balloon, why would that rise? So the reason is that only, that air is heavier than helium, let's say. So let's say this is a helium balloon. So this helium balloon will have weight less than the upthrust. So the upthrust is going to be more than the weight, and therefore the helium balloon rises. So for air, this upthrust the air is providing is even more than the weight. It's not for you. For you, it's always the weight more than upthrust. That's why you're not rising. But helium balloon is so light that upthrust can even be greater than the weight, and that is why it starts rising. Helium is a very light gas. You do understand that. So keep in mind, this upthrust is also valid for air or gases, but it's not very prominent or as prominent as in case of liquids. Okay, the upthrust of water makes you float in the swimming pool. So now you understand why do we float. That's because of the pressure difference. We feel a net upward force. I will wait and then we move forward. All right. So now the part that I was talking about, that we have to discuss free fall without air resistance and then with air resistance. So very quickly here, but one point of confusion that many students would have is that the sign convention. So normally if there is a person who's falling freely, which is very evident from this person's face, that this person is free falling, and let's say there is no air and it's vacuum. Okay, it's vacuum. So in vacuum, everyone is pulled down with the same acceleration. So acceleration does not depend on mass, as you have learned. So even if it's a feather or a coin, can you imagine, in vacuum they both will fall at the same time. So the acceleration is going to be same for all. So now the point of confusion is that you normally would take downward positive because you're falling. So that is the normal convention, but I wish to discuss the other convention as well, just for the just to clear that confusion. Okay, So let's talk about acceleration first. Let me take a straight line shape. Okay. So what is it? Acceleration. If I take upward positive, then you would say it is fixed at 9.8 meter per second square or 10 meter per second square approximately, but it remains constant. So it is a flat line. But when you talk about velocity, let's say, when you talk about velocity, so what should it be? It should be a straight line with a uniform gradient. So velocity is obviously increasing, and that is increasing at a constant rate, and that is why it is a straight line. But when we talk about the displacement, okay, so it has to be like this, and you can imagine why. Because the gradient, the gradient is in accordance with velocity, displacement versus time. All this you should know. If you don't know all this, that means you have to watch the motion videos first. I have specifically made a class on gradients, what gradients reveal, how they are to be interpreted. You should all watch that, okay, before seeing this. Okay, so the gradient is in accordance with velocity. So the velocity is low, and then the velocity is increasing, and so is the gradient. So the displacement versus time graph would look like this. But again, just for the sake of doing it, that if you take upward positive, okay, I will erase these, but just for the sake of doing it, then the acceleration should be denoted by negative 9.8, and then the velocity graph will also be like this, and the displacement graph will also be like this. But all these are true only if you take upward positive, and since you know that all these things are in the downward direction, so then they are to be taken as negative. But we normally don't do that, okay, we normally don't do that here. So I am omitting this, I'm removing this, and we are going with the normal sign convention that if the body is falling or going downwards, we take that as the positive. Okay, so all these three graphs should be very clear. You draw them very quickly, a freehand drawing. Very important to keep drawing and writing. That gives you even more retentivity. You retain more just only by looking at the video, or like watching the video and looking at the board doesn't make sense. So keep writing the important stuff for high retentivity. All right, next thing. So with air resistance now. So what are we discussing now? Free fall with air resistance. Think about it. This person has started falling due to gravity, but now air resistance comes into picture, and that air resistance is increasing with speed. So as the person is falling, definitely its speed is increasing. Let's set the chronology right away. The speed increases, so the force of air resistance also increases. So this remains fixed in magnitude, but this red arrow keeps on increasing, okay, due to which the net force, that is this minus this, keeps on decreasing. And since net force is ma, acceleration also keeps on decreasing. So let me revise this again. As you're falling, what is happening? The velocity is increasing thanks to gravity, but no thanks, sorry, because this is not very ideal to fall like that. But let's say when you are falling, the velocity is increasing, so the air resistance becomes more prominent, and due to that the difference between weight and air resistance starts reducing, and therefore the net force starts reducing and acceleration also starts reducing. So expect this first, that acceleration versus time graph should be like this. You start off with a value, let's say 9.8, but you won't be able to maintain that. Why? Because air resistance is now existing, and ultimately I've touched the graph here. What does that mean? That at one point the force of air resistance becomes so prominent that it becomes equal to the weight of the person, and then the two forces become equal, and we would say the net force becomes 0 and the velocity becomes constant. So after a point, don't worry, even if you are free falling, after a point your velocity will stop increasing and you will attain a terminal speed. you will attain a terminal speed. So, can you relate with this graph now? Of course you should. The gradient of this is, in accordance with acceleration. Acceleration is reducing. So, I am not saying speed is reducing. Speed is still increasing. But the rate at which speed is increasing has to reduce. So, it is a little confusing. Speed is increasing, but the rate of change of speed is decreasing. That's why it's more gradient, and then the gradient starts reducing, and ultimately the gradient becomes 0. And we will say that a terminal speed has been achieved. Keep that in mind. This graph is very, very, very important. Though this terminal speed again depends on the surface area of the person, that is very important. So, if the area is more, then this force increases very quickly, and then the terminal velocity will be less. If the area is less, then the terminal velocity will be more. What about the distance? So, distance still would be like this, distance or displacement. Why? Because the gradient still has to increase. Speed is still increasing. So, distance is also increasing, and the rate of change of distance is also increasing. So, the distance graph, maybe it will not be as steep as it was in case of without air resistance, but still it will be like this with an increasing gradient. Keep this all in your head. This is very important what you are seeing right now. I will wait, pause the video, re-watch it. There is no problem if you skipped some part, you got distracted. It doesn't matter, you have an option, you can re-watch the stuff. But all the information that I have given right now is very crucial. Alright, so you must have paused the video and copied down the stuff. Now, the last part of today's class. So, today's class is very brief. I have not accommodated any numericals because this is more of a qualitative study that we wanted to do today. Okay. So, even the questions, the type of questions that you will have here will be more of conceptual questions rather than some numerical problems. Okay, so I wanted to talk about this parachute thing as well. So, what happens when you are, in case of like you have a parachute as well? Okay, so what happens there? Okay, is what I wish to discuss. So, when you jump off the aeroplane or whatever it is, then you do not open your parachute right away. So, the initial part is still the same. So, we are only discussing the speed versus time graph. Okay. So, initial part is still the same, that you start off with 0 speed. Initially, you still have a uniform gradient kind of a thing because air resistance is building up. Right now, you have not opened the parachute, you are in free fall, but then the air resistance starts becoming so prominent. So here we can write that acceleration is almost uniform. For very brief duration, you can take it as, so we can say the velocity is increasing very steadily, but here the air resistance becomes prominent. Air resistance becomes prominent. Okay, and when it becomes prominent, we can say that the net force starts decreasing as we had just discussed, and therefore the acceleration starts decreasing and the gradient also starts decreasing till a point where terminal velocity is achieved. Terminal velocity is achieved, all right, or attained. Okay, so then you free fall with a particular terminal velocity. The skydiver or whatever you may call it is falling with a constant speed for a while, and then they are very trained people, they know when to open the parachute. This is when that happens. The parachute is opened here. Parachute is opened here. Okay, or it is deployed or whatever you may call it. Okay, so then what happens is that it suddenly causes a huge air resistance. Why? Because your speed is already very high, you open the parachute, the area increases tremendously and the air resistance becomes more than the weight. Okay, just like helium balloon. Okay, air resistance becomes more than the weight. So when that happens, your net force becomes upwards and your velocity is downward. You start decelerating now. You start decelerating. Now think just the opposite. When you are decelerating, your velocity is continuously decreasing. So air resistance also starts decreasing. All this while, do remember this, weight is the force that remains constant. So weight does not change with anything, weight remains constant. But the air resistance force now starts decreasing and it again becomes equal to the weight. It again becomes equal to the weight. So this is where the force of air resistance again becomes equal to the weight, but this time it happens at a lower velocity. So it is the terminal velocity again of lower value. Terminal velocity of lower value, which is manageable. So this is manageable, and then they strike the ground and then they finally come to an instantaneous or a complete rest when they fall on the ground. But this velocity is something that they are trained, they know when to open the parachute and attain this particular velocity, and this is well within bearable region, and when they hit the ground they don't get hurt that much. But if it happens at this, you cannot imagine that person will survive. So this particular thing that we have achieved is because of the parachute. Okay, so that is how skydivers work, they function, and it's very fascinating, and you do know the physics behind it now completely. Okay, so there was a lot to learn, not giving you very much details of all this, but just the concept of terminal velocity and the concept of 2 times terminal velocity here, thanks to the parachute. All right, but that's all for this particular class. I hope you enjoyed it, and I will see you further, and we are going to do the previous year questions where we will see how we can apply all this that we have learned today. But that's all for this one. Thank you very much. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.